higher structure in these theories that are interesting to explore. So this is sort of a list of reasons maybe to look at. Now, so there was actually two ideas around to address conformal field theories, which were already known 50 years ago, and in fact very successfully applied in two-dimensional CFT. The first idea is sort of originates both like from the early 70s, is the idea of these conformal partial wave expansions. So that's the idea: you take any correlation function you want to look at in the conformal field theory, and you try to expand it in an appropriate basis of functions, which kind of are adapted to the conformal symmetry. And when you do this, then you see that the coefficients of these things become just constants. Okay, they are constants that contain all the dynamical content. In fact, these coefficients even factorize. You all know this, I guess, from a 4-point function. If you take a 4-point function and expand it, let's say in 2D CFT in terms of conformal blocks, the coefficients are just constant. They're a product of 3-point couplings. Okay, so that's a remarkable structure because sort of this complicated dependence of the correlation function on the insertion points of the fields actually splits off into something that is kinematically determined. It's just the property of the conformal symmetry, and some constants which contain all the dynamics. And that's very special in conformal field theory, this feature. So that's a very powerful, interesting tool. And then a second idea, of course, that I don't want to review here. I think Jeremy will explain that better later. Is sort of Polyakov's idea of the bootstrap, which is in some sense to use associativity or some kind of relation that has this beautiful pictorial representation as a way to constrain these dynamical data, these constants, and then self-consistently solve for the dynamics of the theory. And of course, most of you, I guess, know that, I mean, this was famously applied, this whole program, in 2D CFT with Belavi and Polyakov's Zamolodchikov paper in '83, and of course started the revolution in lower dimensional CFT. So the question is, I mean, so when you look at this, of course, conformal partial wave expansions and also the bootstrap, I mean, this was not initially not formulated for 2D CFT, but it's there in any dimension. The question is, of course, I mean, what are these what are these conformal blocks? What is this adapted basis of functions in which I should expand a conformal correlation function in order to expose these dynamical constants? Of course, in 2D CFT we know very well what the blocks are, and so the question is, in higher D, can we also answer that question? And then, of course, the other question that, in particular, if you're very experienced with two-dimensional CFT, there's this general law that you can solve crossing symmetry constraints because of the infinite dimensional symmetry. Of course, once you go beyond 2 dimensions, you don't have infinite but only finite dimensional symmetry. So the equations, the bootstrap equations, start to look much more complex, and that's another thing to worry about. And I guess again we will see more about this in Jeremy's talk. So the two questions that guide this talk, or in fact this talk and the following talk by Jeremy, are the question: what kind of functions are these conformal blocks that we need to expand our correlation functions in a higher dimensional CFT? And I will actually address this question for any number of insertion points and even the insertions of Wilson lines or line on surface operating interfaces, things like that. So, and the second question is, can one actually make the conformal bootstrap program work in higher dimensions? And of course, those of you who have followed a little bit sort of development in the last 10 years, they know that there has been considerable progress on these things. So starting from 2000, people started to be able to answer, at least in some corners, this question: what are these functions, what are these conformal blocks, in particular the work of Dolan and Osborne. And then once this question was answered, at least for certain examples, there was also progress in analyzing these crossing symmetry equations, and a lot of data has been obtained from it. So as I said already, I will devote, the second question on how you actually make the this bootstrap program work in higher dimensions. It will be discussed in Jeremy's talk after. Here I'll focus on the first question. I mean, what are these conformal blocks? What kind of functions are they? And I will kind of try to embed that into a context, of course, for this conference, into a context of integrable systems. So to sort of give away the main punchline, it turns out that these conformal blocks actually are wave functions of some integrable systems. And we will kind of look at that first, sort of from the general perspective. It turns out that they can be sort of understood in the landscape of Gaudin models where they sit, and then we will zoom into and understand a little bit better what type of wave functions appear.
Is that a general statement, or is it true for specific?
No, this is a completely general statement. So in fact, so what I will show is that whatever conformal block you may need, even if it's for Wilson lines, Toft lines, they will always be wave functions of Gaudin models. In fact, not general Gaudin models, but I will show it will be limits of Gaudin models, very special limits of Gaudin models, which in fact simplify the models. And then we will see some of the more specific, not so general statements that in some cases models of various types. Okay. So here's my outline. On a request from Gleb, I'll introduce you first to conformal field theory in higher dimensions. I imagine that many of you are quite familiar with this, so I'll use this occasion to also maybe sneak in a few ways to think about things that makes it easier to see the Gaudin models emerging later on. Then in the second part, I will describe this kind of general theory of conformal blocks. I will make this link to the Gaudin models and show the limit that one has to consider, and then I'll have a bunch of examples, mostly for a small number of insertion points, where I can make this much more concrete, and you can also get a glimpse of how far the solution theory is actually developed. Okay, any questions? So it's late in the day, so I invite you to ask whenever there is something that's...
Do you need the infinite symmetry at some point? Or?
No, there's no infinite symmetry.
I see, but without infinite symmetry, maybe it's not so easy.
So this was, of course, the traditional way to think about it, right? But I mean, you can also think about it differently. So the infinite symmetry in 2D, of course, means that there's also some kind of infinite degeneracy in twist somehow. You have infinitely many things that have right-moving dimension 0. And so there is actually some kind of very high degeneracy, and that's why you need the infinite symmetry. In some sense, in higher dimensions, you break this.
You can think about.
But okay, let's maybe again I defer that to Jeremy's talk. You will see a little bit what the idea is, how you compensate for the absence of this infinite symmetry, right? So in some sense, the two-dimensional is also more...
You have algebra vector fields, and this algebra is infinite.
Yeah, but I mean, here's the symmetry algebra that I'll discuss. It's always finite dimensional. All these blocks are really blocks for the finite dimensional conformal group, which it has 15 generators if you work in 4 dimensions. Okay. So even that is has been for a long time an open question. I think when people wrote this down in the 70s, they had some integral formulas for these blocks. Right, but they had no idea what functions these were. I mean, they could not integrate, and in fact, that was the problem for the field to develop, and that's why nothing really happened until 2000, when people were getting. So that's actually a non-trivial question. So okay, so now comes my class on conformal field theory. So as I said, I will be in D dimensions. So the conformal group, I will work with the Euclidean conformal group. So I have imagined. So most of my construction will be fairly algebraic, so it doesn't really matter about the signature. If you have questions on that, we will. So the Lie algebra is SO1, D plus 1, and it has a bunch of generators. Of course, there's rotations, translations. That's the standard Euclidean symmetries, and on top of that, you have dilations, and you have special conformal transformations. And so I invite you to always think of 4 dimensions. So there's 4 translations, 6 rotation generators, right? It's SO4, 1 dilation, and 4 special conformal transformations. So that makes 15 conformal transformations. Okay. Now this conformal Lie algebra, or the corresponding group, has a number of interesting subgroups that will play a role. I'm just introducing them here. So we will be thinking, of course, about inserting fields at a point. So it's interesting to know what the stabilizer is of a point, right? Which conformal transformation stabilizes the point. You can take the point to 0, and then you see it's stabilized by dilations, rotations, and special conformal transformations. So that's a semi-simple group. It's a direct product here. And so the quotient of the conformal group by this stabilizer group of a point, of course, is RD, which is kind of the movements of the point, right? So similarly, you can think of the stabilizer of 2 points. That will also play a role later on. So now you imagine you send one point to 0, the other one with the special conformal transformations to infinity. Then you still have dilations and rotations as symmetries of 2 points, right? And the quotient of GD divided by the stabilizer group of 2 points is R to the power of 2D, which is really the movements of 2 points in the d-dimensional space. And for those of you who like to think about defects, I mean, you can actually also think about the stabilizer group of a line, of the Wilson line, a conformal Wilson line, or things like that, where a defect of dimension p+1 is given by a conformal transformation parallel to the defect, times transverse rotations, and also gives rise to a moduli space of deformations of this defect. So for instance, if you have an interface, conformal interface, you can think of it as a spherical object, and it has d+1 parameter. One parameter the radius, and the other parameters are the position. So again, I will make a few comments on these higher dimensional non-local operators, because I know some of you are interested in this. I will not kind of don't want to confuse you. All right, so that's conformal algebra, and I assume that you have some idea what these Lie algebra relations look like, right? There's some kind of raising operators, the p, the momenta, like differential operators, and then k, the special conformal transformations. You can think of lowering operators because they lower the degree, the eigenvalues of d. So the next notion is the notion of a primary field, and I think you probably also have seen that before. So a primary field, so in the space of all fields of a conformal field theory, there are fields which are derivatives of other fields and fields that are not derivatives of other fields. And the fields that are not derivatives of other fields, they're called primary field. And they have this commutation relations with respect to the conformal generator. In fact, most of these formulas I expect you have seen before. The simplest is one that tells you that the field has scaling weight delta, right? And delta is conformal weight or scaling weight of the field. There's another quantity here that's sigma, that's related to the spin. If you have a field with spin, for instance a vector field, then of course it transforms non-trivially under rotations, and that's encoded in this matrix. So fields typically can have a weight and a spin, and weight and spin are basically representations of the stabilizer group of the point. Okay, that's what you have. So the weight and the spin of a field that you have in your two-dimensional conformal field theory give rise to a representation of the stabilizer group of the point, and I will call this representation pi delta lambda. Right, that is a bit too small for people to see, but that's what's written there. So there's actually a way to realize the representation that corresponds to a primary field in terms of just functions on a group. Okay, and so this is the first kind of intermezzo that is maybe not a standard CFT 101. So how do I do this? I can take actually all the functions on the group, and I make them take values in some finite dimensional representation of my stabilizer group as star. In fact, the representation that corresponds to the choice of delta and lambda, right? So there's a representation. So if I have a vector, this would be a d-dimensional representation space, right? And then dilation acts on it with returning the eigenvalue of delta, the way. So I can take then all functions which have this property that if I multiply with an element from the stabilizer group from the right, that they transform covariantly. So I can take the right multiplication of the stabilizer guys out and use them to rotate sort of the function, which is a vector-valued function. Okay? And now you can do a simple exercise. You can actually check if you take the space of these functions, right? It's a linear space of functions on the conformal group. If you take this linear space of functions, you can, of course, introduce an action of the conformal group on this linear space of functions by left multiplication of conformal group generators. And you can work out how these things transform. And I did this here, this here for the dilation operator. It's a bit symbolic, so I think of this function as a function of just the translation generators, because everything else I put into the is in the stabilizer group. And so when I now act with D from the left of the dilation generator here, I can use Baker-Campbell-Hausdorff commutation relations of D against the P's to bring the D on the other side. And then I can use the covariance condition here for the dilation generator, that's this one, to take out this piece, and this becomes just a derivative of the function. You see that this function here, function on the conformal group, evaluated e to the IXP, has precisely the same transformation behavior as the primary field. Okay, that's a way to build objects on the functions on the group that behave like a primary field. And of course, this construction here is the famous construction of continuous series representation, and that's what happens. So you can do actually the same, use the same also for defects, then you just apply the same construction, and you also get a bunch of differential operators, a little less well-known differential operators that describe how a primary field course generating a defect to a line or so, how they transform. Okay, that's primary fields.
Yeah. Question. In 2 dimensions, the spectrum of dimensions of primary fields is discrete.
Yes.
Why it's
Not necessarily.
Yeah, sorry, not necessarily, because we have also like Liouville theory or other non-compact models, so it's not always discrete. But of course, in rational models, it's discrete.
in rational models is finite?
So here, of course,
In rational models is finite.
sorry, it's finite even. Yeah, it is finite. And
Generally,
in some ways,
for
discrete
series
and
and one,
infinite,
it's
and then they-
discrete.
yeah.
And in this, in the high dimensional case,
So I mean, think of the 3D easing model. I mean, you can look at Monte Carlo simulations, compute the spectrum. It's also discrete, right?
Yeah, that's what my question is. It's a numerical fact, experimental fact that it's discrete, not continuous. Or there is some arguments. Or there are some arguments because if the spectrum is not discrete, there is no reason to talk about primary fields really.
It makes sense to talk about prime. Again, these are non-derivative fields. I could be on top of them.
Continuous spectrum.
But yeah, I mean, I don't know. Maybe I'm wrong, but I don't think of a higher dimensional CFD where the spectrum is not discrete. I think it's fine to think of it as discrete, right?
What is so wrong with Liouville? In Liouville, so you have integral of 3
Yeah.
functions. I don't know.
I think it's discrete.
Maybe we should let you
Okay.
solve the 3D icing model first, and then maybe let's generalize later on.
But of course, in terms of representation theory, I mean, the conformal group does admit the continuum of the other, right? That is very different from, let's say, Virasoro at central charge less than 1, which discretizes from the beginning. Here, of course, there's no constraint coming from the. So the next thing I want to talk about is correlation functions. So now let's suppose we take a correlation functions where we put specialize now just n primary fields, and of course that satisfies conformal water densities, which is a statement that when I hit with the sum of these differential operators that I displayed on the previous slide, then I just get 0. And that typically gives you well, for every generator in the conformal group, it gives one constraint, right? So it reduces. But of course, sometimes these constraints are not independent. So the maximum number, like if you have a correlation function in 4 dimensions, you get 15 constraints, but they may not all be independent. And of course, these constraints you use to write the correlation function as a function of cross ratios only, not as a function of x. So then you, of course, all know that once you have a 3-point function of primary fields with conformal transformations, you can actually bring that to standard form. So this is a 3-point function of scalar primary field. It always looks like this. Okay, I think most of you have probably done this calculation. And it's also clear from the conformal symmetry, right? If you have 3 points, conformal symmetry can bring the first one to 0, the next one to infinity, we just set there, and then you have rotation and dilations that bring the third point sort of in the axis from here to infinity, like just here at the end of the blackboard. And then you still have actually rotations left in the space around these axes. So you don't even need all the conformal symmetries to bring it to this form. And so this is what it looks like. So in the following, I'll just, so this function of the x's I will just denote symbolically by this symbol. It's just a known function, very simple function. In fact, you can do the same for if one of these fields is not spinning. Let's suppose this field phi 3 actually carries spin as a vector field or a stress tensor. You can still compute the 3-point functions also uniquely determined up to a constant. And the symbol, I mean, the function here looks a little more complicated, but it's known explicitly. You can look it up even in the classic books, and then you note it by this symbol. Okay, so it's a function, a matrix value function that describes a 3-point function of.
What is STT?
Sorry, yeah, so I didn't say. So that's a symmetric traceless tensor. So if you have two scalar fields, when you take the so STT basically means a particular subset of rotation representations that you can get only the symmetric traceless tensor representations. You can get, in fact, all the other. It turns out that all other 3-point functions have to vanish if you have two scalar fields, and the third one is in a non-trivial spin representation that has to be a symmetric traceless tensor representation in order for this to be non-zero. Otherwise, the constant will keep it. Thank you for the question. Yeah. So let me say one thing, because the first time I saw that, in fact, in 2D CFD, I was quite shocked, because we always think like when we have 3 primary fields, we can always compute the 3-point function of a number. But that's, of course, not true, even not in 2D CFD. For instance, if you have two fields which carry spin, and the third one is scalar, then it turns out that you can only fix this up to a finite set of coefficients, and the number of coefficients actually grows with the spin of the fields. And there's an easy way to see this, and it's actually, so I said, let's say in 4 dimensions, you have a 15-dimensional conformal group. Now if you have a field with spin, so you have creation operators, right? I mean, creation operators in this field, I mean, first of all are the derivatives. These are 4 creation operators for every field. And then you also have 2 spin creation operators, because your SO6 has 2 creation, 2 annihilation operators, and 2 carton. So you have, for generic representation, you have 6 creation operators that create sort of descendant fields somehow from the primary. So this one has 6 creation, this one has 6 creation, and then this one here has only 4 creation because it's a scalar field. So total the number is 16 creation operators, but you have only 15 word identities, so you cannot use the word identities to completely fix the 3-point function. There's some finite number, and finite is an interesting finite because when you make the spin very large, it becomes effectively infinite. Okay, and that's going to be very important later. So good. And now comes the last part of my CFT lecture. As you all know, is in the CFT, the operator product expansion operator product of fields has a convergent expansion. So for instance, if you have 2 scalar primary field, it kind of reads like this. You can expand that in the sum over primary fields now of spin in these symmetric traceless tensor representations, and with some constant coefficients, which are essentially related to the 3-point functions that we had before. And then some differential operators acting on the field. And these differential operators basically contain the sum over all the derivative fields, or descendant fields, right? So there's an infinite order differential operator, right, that encodes sort of how precisely in the OPE the primary and all its descendants appear. And these differential operators you can compute, right? So I gave you here an example for such an operator when the primary field is itself scalar. This is what the first few terms look like. And this is explicitly known, and you can work it out to any order. And in fact, even Ferrara Griselgato did this already back in the 70s. So that's it's known formulas. So you have the operator product expansion, and then of course the last idea is that now you can use that to compute higher correlation functions. For instance, if you have a 4-point function, you can take the first 2 scalar, that's 4-point function of scalar fields, the first 2 scalar fields, you insert this OPE, you get a sum over primary fields, but then with these differential operators acting on them, right? And so you can take the differential operator out, and you have a 3-point function of this higher spin field and the two scalars, 3 and 4. That's this function here, which I told you is a known function, although I didn't show you what it looks like. And then you act with this infinite order differential operator, and you get this form. And this is, of course, the conformal block expansion that I started off with in the beginning. So this object here is the conformal block. It's some complicated function of the insertion point x3, x4, and y. But of course, and then coefficients which are just constants in front. But this quantity here satisfies the conformal water identity, so this object also has to satisfy conformal water identity, so it must be a function that only depends on the cross ratios. Okay, so in the case of 4-point functions, there's only 2 cross ratios. So 2 cross ratios comes, I mean, we said when we have 3 points, there's no cross ratio. When we have a 4th point, we still have rotations around this one axis to bring it into the floor. So then we have one complex parameter, 2 real parameters to parameterize. And these are the famous cross ratios that I guess you can see in the back. So there's a bunch of functions here that depend on 2 variables, these 2 cross ratios for 4-point function. They of course also depend on quantum numbers delta and L, which are sort of the weight and spin of the intermediate field that appeared in the OPE. And they depend on the choice, of course, how we did our expansion, that we did the OPE first between 1 and 2 and then continued. And in principle, these things you can compute, right? If you have a formula for this, you have a formula for this guy. I showed you some example, and you can now go ahead and compute order by order terms and hope to resum. So it's a valid question. This function, what is it actually, right? What type of function do you get?
Can it be degenerate as in 2-dimensional case?
Sorry?
Can it be degenerate as in 2-dimensional?
So 2-dimensional case, so you can do this also with the ordinary, 6-dimensional conformal group in 2D, right? And in that case, it's a little easier to answer what you get. Mm-hmm. And in that case, you can compute these things by some kind of classical integral formulas. It's relatively easy.
Very hypergeometric function.
So yeah, in 2D, these are just ordinary hypergeometric, single variable hypergeometric function, of course, or products thereof from left and right movers. So this you can compute by elementary means. This people could already do in the sample set.
This is written for Minkowski or Euclidean theory?
So I have now chosen Euclidean signature. So we will first do this in Euclidean, and then we will talk later in Jeremy's talk about the structure of these things when we go to analyzing. Okay. So good. So this is where we are. So I've introduced now these objects that we're after, and the question is, what are they? Good. So now let's shift gears. So I kind of leave my CFT introduction to CFT lecture. I actually spent half an hour on it, right? So, yes. Okay. Good. And now I want to look at this problem through the eyes of these 3 gentlemen who received, I guess, together the Danny Heinemann Prize for Mathematical Physics in 2009 with this combination. And in fact, as you will see, these 3 are particularly useful or will appear prominently in the following discussion. Actually, I'll start with Gaudin, and then later I will come to the other. So let's summarize what we have seen. So now I kind of zoom out a little bit again, so we saw in the previous discussion that, of course, there is a way to introduce these conformal blocks, and in principle we know they should be possible to compute them by just conformal kinematics, just group theoretic quantities, and they have a bunch of labels. First of all, they are functions of the cross ratios, depending on how many cross ratios you have, 2 for the 4-point function. They depend on some internal labels, like the spin and the weights of the exchanged fields. And they depend on the choice of this OPE channel, like the way how you actually decided to compute your correlation. So examples. Now I do this in D larger than 3, just because in D equal 3 there's some accidental changes that we can also discuss. So for 4 points we have already discussed this. We have 2 cross ratios, and there's also 2 labels, right? So the 2 labels, spin and of course the number of cross ratios, the number of labels has to agree, because we are after, these are kind of roughly a basis of objects in which you want to expand. So like in the Fourier basis, right, if you have functions in d variables x, you need d momenta, the basis of functions in d momenta. So it has to be the same number. And of course, for 4-point function, you can have different channels. I mean, for instance, here you have 1 and 2 OPE, you take first, here you take 1 and 4 first, and that's a different channel. Now let's go to 5-point functions. In 5-point functions, so now you can go and compute the number of cross ratios for a 5-point function in 4D. So we had two for 4-point function because we had used this rotation around the line to bring the thing to the floor. If we have another point, we still have an SOD minus 2 left, which we can bring this point to a 3-dimensional space. So we have the five cross ratios, and that exactly matches with the number of labels. So we have the spin and weight of the exchanged fields, that's 4 labels. And then I told you before that when you have 3-point functions, which have 2 spinning fields and 1 scalar field, then there's kind of 1 extra label attached to it, because I told you that there's a finite set of constants that are undetermined. So in some sense there's 1 extra label attached to that, so there's 5 labels here and 5 cross ratios. Now for a 6-point function, it looks like this. So you maybe you can tell me in the 6-point function in 4D how many cross ratios you expect to get. 9 cross ratios, right? Because you just have no more symmetries to the 6th point, no more symmetries to make it anything special.
Maybe that meant that they cannot tell you 9. Like you can't.
Sorry?
Sorry, that was. Well, the answer to the
9
question
in
was
German
9.
is no.
Yeah.
Which,
9. If you, 9 is correct. In German, 9 means no. 9 is the joke.
Oh, yes, thank you.
9.
So far away in that brain. So there's 9 cross ratios and also 9 labels. You can tell me. This is kind of big. So there's 9 labels, right? There's here the spin and weight of these fields, and in the middle in 4 dimensions, symmetric traceless tensors is not in 4 dimensions, not the most general spin representation, because you have SO6, you have 2 Cartan generators, you have 2 spin labels. So you can have 3 here, and then you can have 2 of these vertex quantum numbers, and that also makes 9. And then finally, just for fun and so that you practice, so here's another way of writing the 6-point blocks. Actually, in this case, 6-point is the first time that you can have channels of different topology. That's called a snowflake, very fitting with the weather outside. And so how many cross ratios?
What number of points? 9.
Same, right? Because it doesn't depend on the choice of the channel. What depends actually the distribution of labels a little bit. So you have here only symmetric traceless tensors can appear as in the exchange. So you get 6 parameters, but you still need 3 more, and somehow this vertex here has actually 3 of these integers attached to it. And thus you can also count if you have 3 representations that all have 6 raising operators in 4D, then you can make 18. 18 minus 15 is 3, so there must be 3 labels attached to the vertex. Okay, good. So I see that you're still with me. That's actually, okay, so now that we practice a little bit the type of things that we are interested in, I mean, we want to understand these functions of many variables with many labels, and now let's look at how to construct them. What's the relation with Gaudin models? So first of all, we can now use the data that we have to introduce a Lex connection for Gaudin model. So we built this usual formula. Now what's here? So this is a family of first order matrix valued differential operators. So what I put here is the sum over sites. Let's say if an endpoint function there's n terms that I include here. Then here I put my first order differential operators that I use to describe the primary field. So I multiply them with matrices and like fundamental representation of my conformal group. So this would be in 4D would be 6 by 6 matrices. And so I built this thing. I introduced also some kind of extra parameters Wj or omega j, which are some sort of inhomogeneities. That's the standard Gaudin construction. And then I can decompose that in the spaces of conformal generators. So alpha runs from 1 to 15 in 4D. And then, according to work of, in particular, Fagan, Franco-Ricci-Tichy, one can show that you can basically take these guys, you can truncate them. So each of them is a first-order differential operator, right? You can contract the indices, get the lower indices by the invariant tensors of the conformal group, like second order, fourth order, whatever. And then you can also find lower order corrections such that that these guys actually form a commuting family of Hamiltonians. Okay, for any choice of Wj and Wj and respective parameter. So that's sort of a famous result, right? So there's a machinery here from the data that we had. I mean, these differential operators to create a set of commuting differential operators, higher order differential operators that act, of course, on our conformal blocks essentially, or on the correlation functions, because they act on the individual fields, right? This is
Can you say again what this kappa is? The kappa. The contract with kappa.
Well, kappa would be invariant tensor, so the killing form, and some tensor that you have in the conformal.
Is it another input for?
Well, I mean, you know, these are classified, right? So for the conformal group in 4 dimensions, you have 3 of these invariant tensors, right? So they're known that you can look at. So it's not something that you have to put in. You just read it off like this, and you plug it into the construction, and you get your operator. So what you have to work on in principle is these low order corrections to just make sure that also in the quantum theory that everything. Now another fact that is actually interesting is that these operators, you can prove that they commute with the diagonal action of the conformal generators on the primary field, which is this combination that appeared in the water identities. So it actually descends. I mean, it initially acts on functions in functions in the various xi's in the primary field, position of primary fields, but it descends basically to the correlation. It's consistent with the water identities. So it actually becomes differential operators that act really on the solutions of water identities, that is on the correlation functions. And so you get some finite set, of course, some finite set of higher order differential, commuting higher order differential operator that act on this space of CFT correlation functions and preserve the water identities. And in fact, it's not well known that there's sufficiently many commuting operators. So there's as many as you have degrees of freedom, independent ones. Now this looks good. It's a kind of cheap construction. Now you can see that you have like all these higher order, second order and higher order differential operator acting on your conformal blocks, on your correlation functions that commute with each other and can be measured sort of simultaneously. But they depend, of course, still on these parameters Wj, which are ingenuities of the Gaudin model. And the other thing that they don't do in general quite well is, so when we want to talk about our conformal blocks, we want to make sure that we diagonalize them in a basis so we can read off some, we can measure. Let's go back to the. Do you have to take this actually?
There's no point.
No, I understand that. So then I go back here. Of course, these conformal blocks, the way I defined them was really they had defined values of delta and L attached to the field that was exchanged in the intermediate channel. And of course, that's something that I want to preserve when I now construct the basis of eigenfunctions. I want to make sure that these are eigenfunctions for which the value of these Casimir operators is given by the values delta and L. So I have a certain set of differential operators that I do want to diagonalize with my construction. And that I know that from the beginning, because that's part of the definition of what a conformal block is. And when I do this Gaudin construction, initially That's not so clear. I get an infinite set of commuting operators, but among these second order operators do I find sort of my Casimir operators that really measure the spin and weight of the intermediate field. And in fact, it turns out that if you want these Casimir operators that measure all these intermediate quantum numbers of the intermediate exchange fields, then that forces you to send these inhomogeneities of the Gaudin model to some very special limiting values. In fact, they have to all be sent to either 0, 1, or infinity. Okay? And the way you do this depends on the channel that you want to discuss. So you choose your channel, and then there's a construction that tells you what you have to do with these inhomogeneities to make sure that the Casimirs for that channel, right? I mean, the Casimir operators depend on the channel because what's exchanged depends on the channel. We saw that with the particular snowflake. And so for each channel, there's some kind of construction that tells you how to take limiting values of these inhomogeneities in order to get the Casimirs, and then, of course, hopefully, extra commuting operators that commute with the Casimirs and complete this kind of system.
Is the order of limits important, or it's?
Yeah, so it's very important how you do this limit, and so you introduce basically the way it's done is that you introduce some new set of Hamiltonian. So in fact, so I don't want to go into details, but so you represent your OPE, it's sort of in a planar rooted tree diagram, and then there's some kind of prescription how to associate to all the vertices, the blue dots here. You can associate a new Hamiltonian, which is now independent of any parameters. It's just one function of the spectral parameter, and then there's some construction how to do this, how you have to scale the W's given by some polynomials fj, how you have to scale the spectral parameter, and it's a construction that we kind of figured out with a lot of contribution from Savant in particular, how to do this. For any OPE diagram, there's a precise algorithm how to compute these data, and then you can take the scale limit of the Gaudin Hamiltonians, and then out comes a system of commuting Hamiltonians, one for each external vertex, which have now only poles, singularities at 0 and 1. The one at infinity, of course, you can't see. And so from these guys, one for each of these internal vertices, you can expand them in this way. You get sort of some higher order differential operators, a set of higher order differential operators. So in these sums, the two extremal points would be Casimir operators that you use to measure the spin and weight of intermediate field, and the ones in between would measure these n integers, the thing that sit at the vertex. And so what we have checked is that this construction, first of all, we've defined this limit construction, all these functions for generic cases. And we have checked that the operators here, in spite of us taking this limit, in principle we could have lost some of the commuting charges, but that's not the case. They still generate sufficiently many commuting charges. And so we get some kind of limiting Gaudin system, right? That is sort of just as good as, I mean, it's an integrable system, and it's somehow derived from Gaudin, but it's not the same as Gaudin. We'll see a little bit more what the simplifications are. So maybe since I'm running out of time, I don't want to go through this. This is just a curiosity. So these limits, in general, I think they were new. These limiting Gaudin systems, I think, were not considered before, except for this case for the... except for very particular channels, these COM channels. It turns out that it's a very cute dynamical system, integrable dynamical system that people, I mean, in particular, Kapovich and Nilsson came up like many years ago, 30 years ago. It describes sort of a system that is a kind of on the integrable system on the phase space of polygons, and polygons in a three-dimensional Euclidean space. It turns out in a way that you can read from the slide, and I can tell you, you can make that into an interesting integrable system. So this was discovered a long time ago, this system by Kapovich and Nilsson, and then later a few people saw that you can actually get this as a limit of Gaudin. So that's sort of an example that has been studied already to quite some extent, but in general, these limits of these Gaudin systems for other types of OPE channels were not introduced before. And I think they
What
are.
are the canonical variables?
So yeah, okay.
On this polygon.
Yeah, I also have another part. So you can ask the question at the end of the talk. So I'm happy to discuss that. It's all written on the slide. So it's a fun system. It's really quite nice and has a very simple computing set of Hamiltonians. And okay, good. So this described. So the purpose of this talk was to embed this problem of finding these conformal blocks for higher dimensional theories, conformal field theories, into the world of integrable system. But of course, it's a vast landscape. I mean, Gaudin is sort of a very general framework to produce integrable systems. And we saw already that we are now going to a particular corner of this Gaudin, which is, in fact, I'll give you more of an idea how special it is, which is then relevant. So it would be too short to say that conformal blocks are Gaudin integrable systems. It's actually a very special limit of Gaudin integrable systems that appears here. And in fact, it turns out that when you specialize even further, like fixed number of points that you want to study, you actually find other interesting models that have been studied before. Which
So number of points is length of the Gaudin spin chain. Yes.
exactly, yeah. So okay. So how much time do I have? Maybe
6 minutes.
6 minutes. Okay. So I'll go through this really fast. So the first thing is that it turns out. So when you do 4 points, which is sort of the standard case, where 4 local fields where you want these conformal blocks, then initially you would realize that, right, the correlation function is basically, you can realize it in terms of 4 functions on the conformal group, which all have this covariance properties that I showed you before. But it turns out this space of functions, in the space of conformal invariance, in the space of 4 functions, actually you can write again as functions on the conformal group, but now spherical functions. So you have 2 invariance conditions from the left and right. And this is explained on this slide. So the upshot is that you can think of these conformal blocks for 4 points always as kind of k-spherical functions. So these are functions which have covariance properties both with respect to left and right transformations under dilations and rotations. Okay. And so when you fix your spins and dimensions, you fix basically these left and right representations, and so you get vector valued functions, or let's say functions in some finite dimensional space that is determined by the spins, with certain covariance properties. And on this space of functions, you can model, you can basically embed your correlation functions in the space of functions on the conformal group. And so this double coset conformal group divided by this K group, again K was dilation and rotation, that's a 2-dimensional space. And this 2-dimension is of course the number of cross ratios. And so then you can try to compute the Casimir operator, this one of these differential operators, the only non-trivial, one of the non-trivial operators that you get from the Gaudin construction in the limit. And in fact, in general, this is a hard computation for generic spins, but fortunately, Harishchandra has done the computation long time ago. You can do this and write down basically some sort of spinning system. Computation that everybody can do, in fact, that's a very easy computation, is when you have no spins. You just have scalar fields. So you do this thing, you take the Laplace operator on your conformal group, and now you descend to this double quotient. Okay, and that's a calculation that is really fun to do, especially if you have the conformal group of 1 dimension, like SO 1,2, that's like 3 Euler angles, and you have 2 covariance, which means you have 2 conditions with respect to left and right translation. So you expect to get something functions in 1 variable in the end, and you can take just your Laplace operator, which is a 2nd order operator in 3 variables, and set some of the derivative to constants, and you get a 2nd order differential operator in 1 variable, and then you play a little bit with it, and you see that sort of this Peschel-Teller Hamiltonian or A1 or BC1 Talot-Versailles Hamiltonian. In fact, the more general case is also easy to compute. So what you find is if you calculate these Gaudin Hamiltonian of this Gaudin limit, one of these operators I had before, you compute it for scalar fields, you actually find find Calogero Southern Hamiltonian for BC2 root system with a very particular choice of coupling constant or multiplicities, which are determined by the weights, scaling weights of the fields, the dimension in which you are. So that means in this particular case, and there's also a way to relate that back. So I mean, okay, I don't want to really. So the upshot here is that if you want to study 4-point scalar conformal blocks, you're in D dimensions, you're mapped to the world of wave functions of BC2 Calogero Southern models with 3 parameters. In fact, now you can see a little bit this occasion I can use to explain a little bit or give a different view on the simplification that we got in the when we took this Gaudin limit, the OPE limit. If you actually compute the four-side Gaudin in general, you get a second-order Hamiltonian, which is known to be an elliptic Calogero Southern model or Zemtsev model, which is much more complicated. And so when you send, I mean, this OPE limit basically means that the elliptic surface degenerates and you get this trigonometric Calogero Southern model. So that's the type of simplifications that the Gaudin limit actually brings about in this particular example. Okay, so since I have no time.
Can you go beyond BC2? Can you go BCN?
Yeah, for different problems. So I said before, if you take two Wilson lines in four-dimensional gauge theory, you get BC3. So, so you can get other, you can realize, if you have high enough dimensions of your conformal field theory, you can get any BCN.
Okay.
So, good. Yeah, we also studied these vertex operators, not just the Casimir differential operators, and also these simple one-variable vertex operators also turn out to be some kind of elliptic Calogero Southern model, which was a bit surprising. But, now, finally, let me very briefly say something about solution theory. Of course, this news that for the 4-point function that it's actually Calogero Southern for BC2 root system is great news because solution theory is very well understood. So it goes back to the particular work of Heckman Opdam. Of course, there has been lots of algebraic constructions, but this is a very well studied subject. You can say about these wave functions almost everything you want to say. So it's in the conformal field theory context, the boundary conditions are slightly different than what the mathematicians studied, but this can also be taken care of. And so these wave functions for BC2 they are relevant. I mean, for the two are well known. So you could of course dream to go further from here and actually construct solutions of the more general objects. Maybe you can ask me a question like what the rule could be to go from n equals 4 to a higher number of n, and I'll say something. So the conclusion is, first of all, the main lesson of this talk is these conformal blocks that we introduced in the CFT 101 that are relevant for higher dimensional conformal field theory. We know now where they sit in the landscape of functions. They are wave functions of limits of Gaudin models, very special limits of Gaudin models, sort of semi-homogeneous limits of Gaudin. And so that's kind of the main message I want you to take away from this talk. And that's sort of more or less the current status of affairs. There's a little bit of things I could say about solution theory, but one thing is for sure true, that in general these blocks have not been constructed in the sense that there's lots of features that I couldn't write for n equals 4. 4 points, they are known, but beyond that it's an open problem. It has some chance to be actually solvable, but it's not solved. And as you will see sort of in the next talk, that actually doesn't stop you from doing already at this stage bootstrap from these insights. As you will see, there's only very special features of these blocks and special limits that you need for the way you want to analyze bootstrap equations. So that's an outlook to Jeremy's talk. Okay.
Yeah, so for these folding polygons, what is the folding polygon
polygons. Oh, okay, sorry.
Yes.
Okay, good.
Now, what the canonical variable and what's the time evolution?
Right, so it's nice geometric actually. Yeah, it's amusing. It's so the way it works. I mean, basically, you take this space of polygons, you parameterize them through some vectors e1 to en, right? So that the sum of these vectors adds up to 0. So that's a closed polygon. And now you choose the length of each of these vectors. Okay, you dial a set of n real parameters that choose the length. So these vectors sit on a sphere of radius r. So each of these things contributes basically 2 variables to your phase space, right? It's, 2 spheres, and then you have a constraint which is 3 conditions. So you have that of course generates also gauge transformation. So you have a phase space that has dimension 2 times n. That's the dimension of all these spheres. Minus 6 from the constraint. Okay. And then the symplectic form, you just take the symplectic form on the 2 sphere. Okay, the standard volume form on the 2 sphere, and that gives the symplectic form on this phase space. And that gives you this Poisson bracket. And then so the Hamiltonians is basically you take these diagonal vectors, starting from here, then this, and so on and so forth. And the length of these guys are the Hamiltonians that Poisson commute. So, yeah.
I have two questions actually. So if I'm talking about, if you have a 4-point correlation function of spinning operators,
Yes.
there is not a single conformal block. There will be many conformal blocks because you have degenerate and intermediate channels.
Yes, that's right.
What then corresponds to the level of this Hamiltonian? You should have additional degrees of freedom. Which
So, sorry, there's many conformal blocks because of these extra tensor structures.
yeah.
Yeah. So yeah, you can. Right. I mean, you can think of this, of course, as an extra matrix degree of freedom in your construction, right? So these
It will be part of the
matrices.
Hamiltonian. It will be part of the Hamiltonian then.
It's part of the Hamiltonian, yeah. So of course, as you know very well, I mean, of course, in the field we usually create matrices for functions of these extra polarization variables, and then you can also write them as functions and more variables, higher order differential operators and more variables. So, but yeah, they certainly, those things are not easy to solve. There's a few cases. I mean, okay, in the CFT community, there is some procedure to kind of construct these things recursively. But in general, I think to find these spinning case spherical functions is an unsolved problem.
Second question, short. So if you have correlation function, spinning operators which conserve currents. That's why I want to put additional constraints on conformal blocks.
Right.
What does it mean from point of view of spin change?
Okay, I don't have a quick answer to this. I'm happy to discuss this. Yeah.
The last question.
Yeah, so since conformal blocks are wave functions of some integrable system, one can expect that they will simplify in separation of variables basis.
Right.
And you mentioned this apparently a couple of times. Can you elaborate?
Yeah. Let me do this. I will have it very good word.
So, I mean, I wanted to ask this question even before you mentioned it on the slide.
Wrong direction. So the thing is, somehow you could imagine somehow in this limit it seemed like okay, maybe. So in fact you can so there's separation of variables, and you can see already, let's say in 1D. In the 1D problem, the separation of variables, of course, is known even for general Gaudin, right? And you get to in 4 points to this Hoyne equation, and more general up for higher n, you get a certain function and then you write the wave functions basically as product of this solution of some complicated differential operators, which are then functions of one of these separated variables. Now, what happens in this special limit that we're considering here is that this function, this function the
Baxter function.
The Baxter function, exactly, that it actually is no longer dependent on n. So it's always the same. So so that is a drastic simplification.
And it's number of sides.
And it's a number of sides. So there's no. So it's always it's just a hypergeometric function in that case. And so one might hope that somehow this property would also help. So when you go to higher D, that actually in some sense you only have to solve some of these building block objects and then put it together in a way that So separation of variables, I think, is definitely worth exploring in this context, and it's mostly because this is not Gaudin, but it is a unit of Gaudin that is extremely special.
I suggest everybody who has still questions left comes down. We thank Volker once again and have a short break.